Welcome to your video on Chapter 14. Chapter 14 is all about oxidation and reduction. Basically, this is your lesson on electrochemistry. And electrochemistry is a branch of chemistry that many people find very confusing. However, it is integral to our daily lives. So every battery that you come across, that's an electrochemical reaction happening. So the batteries in your cell phones, the batteries in your laptops, anything around you that requires a battery, that's electrochemistry at work. So let's get into it. So oxidation and reduction. So we've sort of talked about this a little bit in previous chapters, very, very briefly, but we haven't gotten into any details about it. But oxidation, very simply, is loss of electrons. And one way to think about it is the way I learned about oxidation and reduction being gain of electrons is an acronym that is oil rig. So if I say O-I-L-R-I-G, oxidation is loss, reduction is gain. Oxidation is losing electrons, reduction is gaining electrons. The other one that I've heard is Leo the lion goes grr. And that stands for loss of electrons is oxidation, gain electrons, reduction. Okay? But what I would like you all to focus on in this chapter in terms of determining oxidation and reduction is that with oxidation, the oxidation number goes up. Okay, and then reduction, the oxidation number goes down. And then, in my mind, reduction is the easier one to find because when you reduce something, you make it smaller, right? The simple definition of to reduce something is to make it smaller. So if you're talking about something that has an oxidation number that goes from a +3 to a +2, that's an oxidation number that has gotten smaller. And so a reduction has happened, okay? Now, oxidation and reduction are a paired thing. You can't have a reduction without an oxidation, and that's very important. So if you think that you have, depending on the oxidation numbers that you've written, if you think that you have an oxidation but you don't see a reduction, then you may need to recheck your work, okay? So oxidation numbers have rules, okay? This is very important. This is a set of rules, okay? Very much like when we did Lewis structures, we had rules for drawing Lewis structures. Oxidation numbers, assigning oxidation numbers have rules also. Now, a very important thing is that oxidation numbers are not the same as charge. Oops. Do not equal charge. Okay? They're not the same thing. Now, quite often, the oxidation number is the same thing as would be the normal charge of a particular element. Okay, and you see in this box over on the right, number 4, most of the like fluorine, chlorine, bromine, iodine, oxygen, they all have the same oxidation numbers that they would normally have as ions. Okay, but we're going to find that quite often elements outside of those groups will have oxidation numbers that are different from their charges. Okay, so oxidation number is not the same as charge, although they are often the same number. Okay, it's very important to realize that they're similar but not the same. Okay, so let's take a look at assigning oxidation numbers. Okay, so if you haven't done this part, written these parts down, so any element in their elemental form, sorry, having reading is great right now. Any elemental form oxidation number is 0. That's things like solid metals, or the diatomic molecules. Diatomic molecules. Okay, if you remember those, it was I brought clay from our new house, right? And these are all I2, Br2, Cl2, F2O2, and 2H2. Boy. Right, remember all those? Those are all included in that elemental form thing. Also, things like solid carbon, right? That's what's in your pencil leads, right? Graphite is solid carbon. So anything in its naturally occurring state has an oxidation number of 0. All right, monatomic ions. So things like Na+, or Cl-, or magnesium 2+. They will have the same oxidation number as the charge of the ion. Okay? So polyatomic ions, the oxidation numbers must add up to the overall charge. 0 for neutral compounds. And we'll sort of get into that as we go. Right? Now, before I go away from this, atomic atoms that have, sorry. So these are the same always. Okay, so oxygen is always a -2 oxidation state. Fluorine is always a -1. Chlorine, bromine, iodine, always -1. Hydrogen is usually a +1 unless it's bonded to a metal. Okay, the others that are always the same are the group 1 metals. Okay, so things like sodium, lithium, potassium. Okay, those are always oxidation states of +1. Right, so, and these rules are all outlined in your textbook as well. So I hope you have taken a look at those at this point, and you're aware of some of the things that I'm saying. All right, so let's go through some practice. So let's identify the oxidation numbers of each element in these reactions. And we're going to underline oxidized elements and circle reduced elements. So in order to figure out what is oxidized and what's reduced, we need to assign oxidation numbers. Okay, there's no other way to tell what is oxidized and what's reduced unless we assign oxidation numbers. Now, the oxidation numbers go for each atom. Ox numbers go for each atom. And that's very important. Okay? So let's take a look at what we have in our line A here. And of course, we always know this, the little question mark always means that there should be an arrow there. A little translation issue with the programming. So silver solid. So solid metals, with the exception of mercury, all metals are solid in their natural states. So solid silver is going to have an oxidation number of 0. Okay, and then our next one is F2. That's one of our naturally occurring polyatomics, or diatomics, excuse me. Naturally occurring diatomics, so it's going to also have an oxidation state of 0. Okay, now let's look at our products. So no longer in our naturally occurring state, we have silver fluoride, solid. So fluoride is one of those ones, most of the halogens will always be -1s, right? And then if I have a neutral compound, everything has to come out to be 0. So if I have a -1 for the fluorine, that means that the silver has to be a +1. Okay? Now, let's think about it. Reduction means to reduce, right? So the oxidation number is going to go down, right? So if my oxidation number goes down, things are reduced. So if fluorine goes from a 0 to a -1, Silver goes from a 0 to a +1. That one went up. Okay, so fluorine has been reduced. And silver that oxidation number went up. Okay, sorry, I'm going to abbreviate because I'm lacking space. Okay, so when the oxidation number goes up, things are oxidized. When oxidation number goes down, things are reduced. Okay, and like I said before, use the word reduced. Things get smaller when they're reduced. Okay, so it's often easiest to identify what's reduced first, then identify what's been oxidized. Okay, but I'm going to take this out because it says to circle the reduced elements. So let's circle the fluorine because the fluorine has been reduced. And then the oxidized element was the silver. We said to underline, sorry. Underline the oxidized. All right, so let's assign oxidation states for line B. Okay, so sulfur is a sort of less known thing, but if you've ever been to a volcano, or if you ever will go to a volcano, or if you've ever seen a documentary about volcanoes, you know that sulfur exists as a solid in nature. So sulfur is going to be a 0. Right? The next one in line is O2. Oxygen is one of our naturally occurring diatomics, so that also has a 0, and each atom of oxygen has a 0. Okay. Now let's take a look at our sulfite, our sulfur trioxide, excuse me. Okay. So each oxygen is a -2. So -2, -2, -2. Okay, because I have 3 of them, right? So in order for this whole molecule to be a 0, I need it all to balance out to 0. That means that sulfur has to be a +6. Okay, so let's take a look. So each oxygen went from a 0 to a -2, and each sulfur went from a 0 to a +6. Those are the things that are changing, right? So if my oxidation number went down, we're reduced. And if my oxidation number went up, then I'm oxidized. Okay, so let's take that little bit of notation out, and we will circle the reduced elements, and that would be the oxygen, and underline the oxidized elements, which is the sulfur. All right, so let's take a look at line C. All right, the easiest one to pick out is that O2. So O2, each atom of oxygen is at a 0 because it's naturally occurring diatomic. Okay, then let's take a look at the CH4. So the CH4, when hydrogen is bonded to a nonmetal, each hydrogen is a +1, and I have 4 of them. Okay, so then in order for that whole molecule to have a total of 0, that means that my carbon has to have an oxidation number of -4. All right, now let's look at the product side. So in CO2, each oxygen is a -2, and I have 2 of them, so -2, -2. So in order for that whole thing to balance out, then the carbon has to be a +4. Now let's look at the water. So water bonded to hydrogen, water's a -2. And then in order for things to balance out properly, hydrogen bonded to a nonmetal is a +1, and I have 2 of them. +1, +1. All right, so let's take a look at how things have worked. So when we decide what is oxidized and what's reduced, we have to pay attention to the oxidation state of each atom. So my carbon has gone from a -4 to a +4. Now, has that number gone up or gone down? And in fact, that number has gone up, right? -4 to +4 means that that number has increased. So that's going to be an oxidation. Right? Now, my oxygen went from a 0 to a -2. So that number has gone down. So it's the reduction. Okay. Now, if we look at the hydrogens went from a +1 to a +1. So nothing has changed for those hydrogens. Okay. All right, so we're going to circle the reduced elements. That would be the oxygen. We're going to underline the oxidized elements, and that's the carbon.